Hello everyone, my name is Stevan and I will be presenting a paper called Vision-Based Extrapolation of Road Lane Lines in Controlled Conditions. My colleagues were Marko Dragojevic, Momcilo Krunic and Nenad Cetic. So let's begin. Keeping vehicle in the right track while driving is a common task for humans as they perceive lane lines with ease. Naturally, one of the essential tasks for autonomous vehicle would be to detect lane lines in order to keep the vehicle in constraints of the left and the right lane. Except for using them as a constant reference in steering controller, they are used as inputs in other driver assistance functions. Example of such system is lane departure warning system. This warns the driver if the vehicle goes over the lane. In higher level of functionalities, it can be used to steer back and center vehicle in the track to ensure greater safety on the road for all participants. Since road lane lines can be easily found in flowed state, affected by various factors caused by nature, for example, exposure to sun, rain, shadows, environment, and etc., but also by humans, for example, like traffic flow, the road quality, and etc. Obtaining lane lines after recognition process on highways and many other roads is a difficult challenge because of these flows. That is why various approaches are considered and revised. There are sensor-based approaches that use lidars and radars for detection of lane marking. This is done by extracting features from point clouds and relying on well-known road infrastructures. These methods rely on scanning upfront and together with GPS and HD maps successfully predict the road features. However, it is very hard to detect lanes with this approach, so most of the modern approaches use vision-based algorithms. We can divide these type of algorithms into machine learning and numerical ones, and they often use cameras. With numerical group, they are model-based, and many of them build mathematical models of the road and use geometry coordinates of the road and camera position. Another group of numerical methods is feature-based, where this paper also belongs. These methods use algorithms to detect characteristics of the lanes, like colors, edges, curvature, and other so-called features. Despite having many advantages, these methods also have critical shortcomings, as they are limited to number. For example, they are limited to the number of detectable lanes, high false positive, and a lot of parameter tweaking while developing these algorithms. That is why latest approaches also use deep neural networks, and these networks give a high precision in the detection of lane lines. Some solutions of this type have taken a step further and even detect whole road markings like traffic signs and other. Problem with these solutions is that they cannot be formally verified, and many car manufacturers avoid using them as a primarily tool for autonomous driving functions. In general, there are numerous papers and approaches to these topics. However, there is still no single most effective solution for industry use. This paper doesn't solve all these problems, but presents simple numerical vision-based algorithm for lane detection. It extracts lanes and edges based on masking thresholds of HLS color channel without any algorithm. Algorithm works in controlled conditions, and therefore it limits its condition to mostly straight lines and favorable weather conditions. This is a combination and variation of already known methods for extraction of lane lines and lane points. This simple pipeline is described here in the following steps, and I will explain them in details in the next slide. Our algorithm is tested against the urban road segments from Novi Sad, as you can see on the image on the right. First part of the pipeline is distortion correction. This imperfection, or so-called distortion, comes from usage of lenses in cameras. Lenses serve to quickly transform 3D image into 2D plane without pinhole model. Since lenses are curved, they produce distortion at the edges. This makes objects have different size, position, or shape than they are in the real world. There are two types of distortions, radial and tangential, and different formulas are being used in order to get undistorted images from distorted images. For the correction of distortion, coefficients need to be found for every specific camera, as cameras can have different manufacturers' mistakes and position of lenses and planes. We used OpenCV to calibrate our cameras with very well-known procedures using chessboard and etc. Next up is usage of region of interest. If we consider that camera is positioned in front of the vehicle, understandably, we don't need upper part of the image to detect lanes, because it doesn't contain useful information. That is why masking a region of interest is a simple yet powerful tool to decrease processing time and apply LiDAR algorithms and produce some reliable data. However, the region of interest that is drawn here and used in this pipeline is not a conventional masking of beads, because these vertices are actually used as a source points for image transformation. By mapping these points to destination points in warped image or transformed image, we can discard the original image size and get almost exactly this part of the image in the planar view, so-called bird's view. The following characteristics of the image enables us to use perspective transform. The greater the magnitude of the z coordinate of an object in an image, or the distance from the camera, the smaller it will appear in the 2D image. Based on this information, we can calculate transformational matrix to transform given set of so-called source points into destination points, and with this we can get warped image. Again, OpenCV has all the tools for this job. And these tools are functions to calculate transformational matrix and functions to warp all points in given region. The images are loaded in the RGB color space. However, in this color space, simple thresholding based on value of the pixel does not give satisfactory result in every situation. That is why exploring spaces like HESV or HLS comes next as a logical step of this pipeline. In this paper, we used HLS, hue lightness or saturation color space, as a base for thresholding. Hue value represents base, color independent of any change in brightness. Lightness is just a way to measure relative darkness of lightness of a pixel. Saturation describes colorfulness, and as the color is more intensive, the saturation is higher. As seen in the image on the right, L and S channels already emphasize white lane lines, and with careful determining low and high values for a threshold, lane points can be extracted even without traditionally used Kenny algorithm. When tested against yellow lanes, like in the image at bottom left, which are also present on the road, these channels do not give similar useful representation. From these figures, we can see that hue and lightness can represent yellow very well, unlike saturations from these figures on the right bottom part of the slide. And with this information, crucial part is to apply a combination of threshold masks from different channels to leave only lane points in the image, regardless of the color. Color thresholding. As I said, finding a right combination of all masks is a very sensitive part, as it contains hard-coded thresholds. A lot of empirical testing and trials are needed to get correct parameters, which is meant by parameter tuning. We have tried out various combinations of color and gradient thresholds to generate a binary image where the lane lines are clearly visible, like in the images on the right. There are more than one way to achieve a good result, but we achieved the best results using only color thresholds with these steps. Properly combining masks from H and L channel, we were able to extrapolate lane lines for both white and yellow lines, respectively, as seen in the image on the right, bottom and top and bottom. The last part of the pipeline is a Hough transform and lane connecting. Hough transform presents a way to find out lanes by identifying all points on the line. This is done by representing a lane from image space as a point in a parameter space. X and Y represent a image space, and M and B represent Hough space or a parameter space, so-called. For detecting such lines, it is important to properly set all the parameters of Hough transform passed to OpenCV functions. For us, two of the most important parameters were Hough votes and maximum lane gap between points, which are to be joined to make a line. Hough transform will return multiple lane segments that need linear extrapolation into single lane. Multiple segments come from the algorithm itself, as even on a solid line it can find multiple lanes based on the parameter. And other reasons can cause multiple segments like dashed lines. For the evaluation of our pipeline, we used method often found in the literature, that is, presenting a result in the form of several frames. In this way, readers can visually compare correspondence between detected lane lines and real lane markings on the road. We also present results in this qualitative way, as you can see from the first image on the right. Half lines based detection of lines do not work good on curved lines, especially very curved or sudden changes as seen in second image. This was expected behavior, and that is why we used sets with controlled conditions. Future improvements can be found in using Sobel operators with thresholding, using polynomial functions to fit a curved line, or drawing multiple smaller ones in segmented transformed image. Furthermore, experimenting with other Colloq spaces and even combinations of those to get more robust solutions represent one of the possible improvements. And finally, to answer the questions that I received. What are the safety mechanisms related to your algorithm proposal? Meaning, in case sensors get saturated or lanes cannot be detected. Algorithm itself cannot provide single solution to handle all the failure cases in safety manner. This shall be done with architectural and design approaches. Meaning is that algorithm should not be responsible to detect saturated sensor, but only aware that input sources has failed or lane detection has failed. Sensor monitoring can be done by ECU that controls the sensor. This ECU should report these kinds of incidents, and alongside it, the algorithm itself should report failure on image reception or lane detection. These incidents combined can trigger a safe degradation scenario for given use case. This could involve different tasks depending on the level of autonomy if the failure happens. To explain this, I can give a more practical example. For example, in L1 or L2, where driver is involved. In case of failure, informational events in form of text on SID or head-up display and or sounds should be issued to inform the user that system is not working properly due to physical or software problem. However, on higher levels where vehicle is in control and relies on this information to steer the vehicle, except this, safety stopping maneuvers shall be activated. These maneuvers are executed on higher ASIL platforms to ensure secure stopping in the stopping lane if we assume that this happens on a highway, for example. And for a second question, although the solution is devised for the controlled conditions, which steps would be needed to enable the solution in the L3 autonomous driving scenario? In my opinion, first of all, the algorithm itself has to be more robust and be able to handle different scenarios I mentioned in which it is hard to detect lane lines. Next, it would require other sensors to perform sensor fusion and check for confirmation of detected road markings, in which I don't mean only lanes. Also, a tight coupling with the planning modules that can issue steering and acceleration command is needed. Connection is in a way that algorithm needs to be extended and modified to provide all data required by these modules. That would be all, and thank you for attention.